team is composed of 2 computer engineers, Christian DeVideo and James Kiesling, and 2 electrical engineers, Marjorie Pickard and myself, Benjamin Welch. Our technical directors were Stephen McDonald, and Mike Smith was consulting on the project. So what were our goals this year? So we wanted to determine if radar technology had advanced to the point where a personal radar system was feasible that could alert the user to any threats in their path. So how do we define the best outcome? So ideally, we would have a fully portable radar system that was capable of multi-target recognition and could warn users somehow of any impending collision. So we did indeed achieve our best outcome. So we have an audio alert system that uses an 80 gigahertz radar board to inform the user if they're going to come into contact with any kind of obstacle in their way. So here we're going to see a short video of the system working. We see Mr. DeVideo over here, represented by the dot on the GUI, and then myself wearing the audio alert system, and then it is informing me of his presence of a near miss. So here we see a small block diagram of the system. We have the IWR1642 Boost, which is an 80 gigahertz radar board from Texas Instruments. We use a configuration function to set certain parameters of the radar, and then this board feeds information to the rest of the system, which first is data processing, which extracts variables from the packets sent from the board. It's then sent to an object tracking function that tracks which objects persist over multiple frames, which then feeds information to the collision detection. The collision detection determines if an object is going to be a danger to the user, and if so, what is the severity of this danger. Once that's determined, it is fed to an audio alert function here, which will inform the user via a pair of headphones the location of the object and how severe the impending collision is.
Those of you who attended the Fall Capstone Symposium may remember that we were using the Distance-to-Go radar board created by Infineon Technologies. Unfortunately, at the end of last semester, we realized that the Distance-to-Go board did not have the features or market availability for us to meet the best outcome for this project. So, in January, we pivoted slightly and began researching other radar boards. We finally settled on a radar board created by Texas Instruments. You can see it here with the antenna array at the top, projecting the radar beam directly out of the board. Our first step was to establish serial communication between the radar board and MATLAB, where we did the data analysis. Then we wanted to make sure that the data we were receiving from the board matched real-world scenarios. But first, we needed to create a graphical user interface, which maps objects detected by the radar board onto the X and Y axis. You can think of it as a bird's eye view, with the user in the center of the X axis. In this example, there is a cluster of objects directly in front of the user, between 1 meter and 4 meters away. In the lower right-hand corner is an LED which indicates potential collisions. It acts as a stoplight, so green, yellow, red. In this example, it's red, which means the user is about to collide with an object in his or her environment. We conducted multiple field tests during this semester. This enabled us to verify that the data we were getting from the board was correct, as well as develop and debug the algorithms, which James is going to talk about now.
So, the heart of our project was the collision detection algorithm. However, in order to begin developing this algorithm, we needed a way to track objects over multiple frames of data. To this end, we created an object tracking function. This function looks at the X and Y coordinates of each measured object, as well as their directional velocities, and uses this information to predict where the object will be in the next frame. It then compares this prediction to the actual measured objects in that frame, and with all of this information, it's able to determine which objects persist through multiple frames. It also calculates the angular direction of these objects, and then all of this information is passed to the collision detection algorithm. Here, we have a visual representation of our object tracking function. As you can see in this example, there are 3 measured objects relative to the user. The function predicts where these objects will be in the next frame, and then compares this prediction to the actual measured objects in that frame. Objects that are an exact match or objects that are a close match, in order to account for measurement error from the device, are considered to be the same object, and they're assigned the same object ID, whereas objects that are determined not to be the same are given a unique ID. Finally, with our object tracking function in place, we were able to begin working on our collision detection algorithm. This algorithm looks at the coordinates and velocities of measured objects and predicts their movement relative to the user. It then uses this movement to determine whether or not the object will pose a threat to the user, as well as the severity of any potential collisions, and it also allows the user ample time to react to these dangers. Here we have a visual representation of our collision detection algorithm. You can see a red field close to the user and a yellow field slightly farther away. These represent the dangers of potential collisions. Objects predicted to enter the red field are considered very dangerous, while objects predicted to enter the yellow field are considered less dangerous. In this example, you can see a purple object is about to enter the red field around the user, and the red object is predicted to enter the yellow field. And so in this example, the purple object would be considered a very severe threat, and the user will be warned of this accordingly.
So once all of the software components of this project were built and tested, we needed to put all of them together into a wearable radar system. So to keep this system as lightweight as possible, we decided to 3D print our radar mount and then used adjustable Velcro straps to attach this mount to a backpack. The backpack would then hold our processing device and portable battery pack. So all of these technical accomplishments that we've talked about thus far in the fields of software engineering, electromagnetics, scientific testing, and computer-aided design have resulted in a wearable radar system capable of detecting multiple objects and warning users of collisions. In this video, we can see by the user wearing our radar system, they are able to safely navigate their surroundings. In this example, the orange objects represent a light pole, the purple objects represent a pedestrian crossing across our field of view, and the red objects represent background noise introduced into our system by interference from the user's body. So as this presentation comes to an end, I'd just like to express our excitement for our acceptance into the annual Capstone Design Conference being held in New York, where we will be presenting this project alongside other teams from across the nation. Finally, I'd just like to express our deepest gratitudes towards all those who have helped make this project possible, namely Stephen McDonald, who has provided us constant guidance throughout the year, Mike Smith, who has given us countless solutions to our technical issues, and Dr. Sunak, without whom this project would not be possible. Thank you all.